just write the subtitles yourself as you speak.
That's my next project, use the Mozilla Speech API to do my subtitles. So, who of you knows what a transformation matrix is? Who doesn't? Okay, so this talk is for the three of you that don't know. Who of you doesn't know what a matrix is? All of you have seen the matrix? Okay. So, matrix is a grid of numbers, basically, like this. Usually, if you want to do matrices in Python, you would use NumPy. Great library does all the matrices you need. Here, I will not use NumPy. I will use my little demo program that implements some matrix-like thing that makes it easier to explain. All right? So we have 9 numbers arranged in a grid. If you've learned about matrices in school, you probably know you can do some operations on them. You can multiply them, you can add them together, you can find the determinant. Who of you knows how to find one? Wow.
For 3 by 3.
Who of you has ever found that useful?
On the test.
On the test, yes. So we don't need determinants, and the software will do the multiplications for us. So it's pretty nice. We can just see what the matrix does. So I have this as a list of 3 lists, a table or an array of numbers. And what matrices are used for a lot of things. Among them is transformations. Transformations of vectors. Who of you knows what a vector is? What's a vector?
For example, one row or one column of the matrix.
Yes. It's a bunch of numbers, right? So let's say I have a vector 3, 2, 1. A bunch of numbers. And these numbers are not useful by themselves. They're useful if you apply them or something, if you give some additional meaning to it. In this case, my 3 numbers will be a point in 2D space.
2D.
A point in 2D space.
This is 2D. 3D.
No, that's 2D.
So yeah, the screen is 2D. You can see the point. It has so the 3 means the x coordinate, how far on the right of that line it is. The second number is the y coordinate, how far up from the other line it is. Very familiar with coordinates, I guess. Right? Okay? So I draw that point. I have the x coordinate here, the y coordinate here, and there's a 1 at the end. It's just there. It's not really useful. It tells me that this is a point for now. It'll come in handy later when I want to multiply something by 1 and I know where to find that. Right? So now I can transform this vector with my matrix. How do I do that? I multiply the matrix, the matrix and the vector together. Right? So matrix multiplication is, in Python has a special operator. Who of you knows the special operator? One person. So it's for matrix multiplication, the at says it's this operator, the at. So I will print m multiplied by the point. And it's a different vector. Alright? I can draw that. And we can see the point got moved up by the multiplication. Alright, now another question for you. Who of you remembers how to do matrix multiplication with vectors? Kinda. Well, this is the one algorithm that I'll actually go through and explain to you how it works. Because it's really interesting. So, I'm multiplying this matrix by this vector, right? And what you do is, well, the result is a 3-element vector. This, like from a 3 by 3 matrix and a 3-element vector, you get another 3-element vector. I've rearranged it a bit to make it easier to explain. So to get this first element, the 3, you take the first row of the matrix, take the 3 once, the 2 0 times, the 1 0 times, add that all together. So 3 plus 0 is 3. Does that make sense? If it doesn't, please shout. This is really important. So to get the 7, I take the 3 once, the 2 times, the 1 0 times. I get 3 plus 2 is 7. Hopefully. Computer knows. And here I get a 1, because this is 0 plus 1. Right? So, yes?
Can you try when you switch point ampersand n, it will be different, I think, because it's not associative, yeah?
Yes, that will be different.
And because on the right side, I think it will be better to explain when the vector will be in the column on the left from this matrix, not above.
Yes, so good point. If you change these around, you get a different answer. Unfortunately, my cool little demo can't explain that. So what happens, I can actually show you, right? If I do point times the matrix, I get a supported operand times, because my matrix only does what I need for the presentation.
Prepared only for this one concurrent. Yes,
so yeah, this is the one thing we will do with matrices, transform the vectors, right? So now one interesting matrix is one that leaves the vector alone. Can you see how we would do that? We would need to take, for the first number here, we would just need to take 1 times the x. For the second, we would need to take 1 times the y, and for the third, 1 times the z. Right? So let's change that. Do 0 here, do 1 here. And this is called the identity matrix, which has the special property that if you apply it to a vector, it leaves the vector alone. Right? Let's say I have a point 2. And I can do the same thing with a different vector. Okay? Are you bored? Okay, so now I will simplify it. I will do some coding. I will have a list of points, and for each point in these points, I will draw on this, draw the point. Okay, let's move this a bit so we can see where these points are. Three different points. I will explain how the matrix is multiplied by that, and I will actually draw an arrow from a point to wherever the matrix takes. All right. So, if I want to take a point and let's say move it up. What would I change in this matrix to move the point up? Moving up means increasing the y coordinate, right? So you take this point, move it up, the y increases. So I need to increase this middle number here by some constant. How do I get a constant? Well, I always have this 1 here. I can multiply that 1 by something to add that something to this number. Does that make sense? Right? So let's take this number, put it up, and now my transformation matrix transforms all my points up. Right? So now a test for you. How would I move them left? Okay, so how would I move them left?
Decrease the x row.
Decrease the x row, right? So I have this x number here, so I need to decrease all of these by a constant, and I get a constant by multiplying something with 1. So let me decrease these, and they all move left. This is really cool. So the transformation matrix, you have one grid of numbers that you can use to apply some transformation to all your points, no matter how many they are. You just multiply the point by this matrix and you get some transformation. So this is a representation of an affine transformation. Of course it can't do everything, but it can do very interesting things. Okay, let me reset. One of the interesting things is zooming. So to zoom the picture in, I need to do what? So if I want to zoom this point away from the origin, I would need to move it in this direction. If I want to zoom this point, I would need to move it out. If I want to zoom this point, I would need to move it out there, right? How do I do that? I multiply the coordinate by something, right? So to zoom everything, let's say in the y direction, I would multiply this 5, this 2, and this 2 by some number. Currently, this 2 is multiplied by 1, so it stays the same. If I increase this, the whole picture is zoomed in the y direction, right? And the same for the x. If I want to multiply this by something, I'll do that. And you can see they're all kind of retreating away from the origin, right? So that's zooming. I actually have one more trick. I can say this one here I will call S, and I will make it editable so I can zoom both at once. Right? This make sense? Okay. So what happens if I make this smaller than 1? Let us read. They will get together. get 0, won't get anything here. If I get less than 1, they're flipped around the origin. So what can our matrix do now? It can move the points. It can zoom the points. It can flip the points. What else is there? You can see there are a few more numbers we can tweak. So there's this number here, which changes the x-coordinate, and it changes it according to the y-coordinate. Anybody knows what this operation is called? It's not very visible with 3 points. Skew, yes. So what I've done, I've prepared some data. I have these phase points, which is just a bunch of vectors, and I can use them here. Okay. And I also have face lines, which is tuples of 2 vectors, right? So I will draw a line between each one. So this will be A, B, and I'll draw 4 lines, okay? And these are all transformed, so I can, for example, move this. Let me get rid of the arrow. So I can move this, I can scale it. And now I can do the shear. It forms the picture like this. Let me start it again. What? Experiencing major difficulties. Okay, so it kind of squeezes the picture, I guess. Right? The other one will squeeze it in the other direction, in the y direction. If I combine them, I can sort of, if I do it just right, rotate the picture. It's still a bit wonky, and I probably have to scale it a bit to make it the same size. Right? Right. So the shear, the skew or the shear itself is not very useful, but it's useful when you combine it so you can rotate the picture. There is some math involved that you can use to find out which numbers to put in to make the picture rotate by some angle. Let's say I will have an angle, and to make it rotate, I will need to put the sine of the angle here, a negative sign here, a cosine there, and another cosine here. Lots of trigonometry. This is something you find on Wikipedia. Put it once and never do it again. Yeah. It's getting a bit slow because of all these explains and multiplications and stuff, but most of the multiplications. Okay. So by shearing in one direction, shearing in another direction, and scaling in appropriate amounts, we can make a rotation matrix. Right? So it affects all of these numbers, and then of course you can move it around. Right? This is actually what was I trying to say? Sorry. Yeah. So this rotation is always done around the origin, around the 0, 0 point. How would I rotate around the center of the picture?
You would first move it to the center, rotate it, and move it back.
Wow. Would that work? So to actually move it to the center, that should be as easy as moving here. And then I can rotate it. Then I can't rotate it.
You have to have a new matrix.
I have to have a new matrix. Okay, so let me do a new matrix. 1, 0, 1, 0, and how do I move again? You put this -5 in here. Okay. And then I have to multiply all this by some matrix like this. And here as well. It is, let's see. No.
Okay.
So what's the error here?
Origin is shifted also.
Yes. So this first did the rotation around the origin, and then moved the result back. What I really want to do is do it in the other direction. So first move it and then rotate it. It's only in part 2, right? Now the interesting thing here is that I can get rid of these parentheses. Now it will not work. I can change the order. And who knows what this means? If I So this means I multiply the two matrices together and then use that to multiply the points. I can say I'll use this matrix only that one matrix, that like precomposed matrix, multiply over points. Right? What does this mean? I take one matrix that shifts points, one matrix that rotates, and I multiply them together to get some other matrix. I'll not show you how the multiplication works with the numbers. It's kind of complicated. Computer knows how to do it, that's fine enough for me. The thing we need to know is that if this result has the same effect as using both of the original matrices. Transforming with one, then transforming with other. Okay, I can combine them into one matrix that combines both effects. And I can combine lots of these matrices together to get moving and rotating and changing the sizes, all of that in a one transformation matrix. Who's lost? Who's bored? Okay, one and two people. That's pretty good for a beginner's talk. So, how much time do I have? 10 minutes. I'll probably do one more. I'll show you one more thing, so we get to vote. One thing I can show you is what's the deal with this one? How is it useful, and what happened? Oh, sorry. Yeah, later. Not using these points. So, what is this one? What happens if I put a 0 there? The other thing I can show you is how to do this in 3D. So, who's for the 1? Who's for 3D? Okay, so let's go for 1. So, if my vector has a 1 here, that means it's a point. It's a position in space. If I put a 0 there, that means it's a direction. So let's say the up direction goes in the y direction, the plus y direction, right? So I can draw zero. Okay, do you see the arrow?
It's a nose.
It's a nose, and that goes in the up direction. And if I multiply that by matrix, it should rotate the same way as the rest of the face. Hopefully. But since it's a direction, it doesn't have a position, it will always stay in this one place. So if I change the matrix, go somewhere else, right? It always starts on the original, wherever else. It doesn't have a position. It just has the direction. So mathematically, if I put a 0 here at this point, that means the translation, the moving, is ignored. Right? This whole column will be ignored. Right? That's useful for things called normals in computer graphics, where the orientation of some triangle is given by this direction vector, which can just rotate around. It can't move. It doesn't have a position. This representation with the position or direction, and then one or 0 is called homogeneous coordinates. You can Google that, see all the theory behind it. Right? So that's why we have the 0 there, or the 1 there, or the 0 there, to distinguish between position and direction. Right? What's the time?
6 minutes to 8.
6 more minutes. Okay, maybe I can do 3D. So I have some data for a cube. It's a bunch of 4-element vectors. So these have x, y, and a z direction. And there's one here, which means it's a position, point. So let's see. I probably get to remove all this. And for A and B in the cube lines. I draw a line from A and B. It's a cube! Right?
Well,
Yeah, it's a cube when you see it from the top. Yeah, that's because I only show the x and y coordinates, and the z is kind of hidden. How do I change that?
Rotate.
Maybe if you went to school and were drawing some 3D-like pictures, they taught you to simulate the 3D by taking the z direction and adding a bit to the x and the y here. Not here, here.
it should be half.
Isometric.
Right? So I take the z coordinate and make it visible by adding a bit of it to the x, a bit of it to the y. Let me explain 2D times A. Right? Now, what can I do with this? That is not very useful, but you can see how I can manipulate 3D vectors, 3D space. What is much more interesting is the rotation matrices in 3D. Right? Translation, like the movement, that stays the same. But you manipulate these parts of the matrix, and it moves. And there's a z. It's not very interesting. There's scale, so you can make the box bigger. You can shear it. That's the wedge itself. Right? So, and that's all the same as in 2D. But rotation is so much more interesting because you can rotate along the z-axis, or along the x-axis, or along the y-axis. So let me go to my notes and give you 3 rotation matrices. This should be called M. And they look about the same as the rotation matrix before, which was a bit like this, but the sines and cosines are in different places. So they always leave one of the axes unchanged. So this is rotating along the y-axis, so everything along the y-axis stays unchanged. That's this little cross here. That's unchanged. The same here for the x. Same here for the z. And when I multiply those, it all is too slow. There's too many matrix operations. Sorry for that. I don't have time, so let me just do this quickly. So what I'm doing here is I'm telling my graphics card to do all the matrix manipulations for me, so it's faster. I can rotate it in Z, against X, Y, against that, right? All I'm doing here is telling the computer, please apply this matrix to everything you draw. Right? So in here, all the points are drawn. I don't have the fancy explain stuff, of course. fancy and slow explain stuff, but it still works, right? And that is how your graphics card manages 3D models. Right? If you play a game, you have a bunch of points, like millions of points that form little triangles, and if you want to move that model somewhere, if you want to rotate it, if you want to make it bigger, if you want to do all of those at the same time, you just have one 4x4 matrix, and you multiply all the points by that one matrix, and that does magic. Right? So I downloaded a model from the internet. Let's make it bigger. Let's get rid of this weird thing. So I have the note somewhere where I downloaded it from, which I need to show you. Because there's a license that says, the author is flowalistic. This is a cute little creature. I downloaded the model, I parsed it in Python, which was not that hard, and if I can get my mouse working, wow. Right? So what I'm doing here is telling my graphics card to multiply all the points it draws, all the lines it draws, everything it draws, by one matrix that I've pre-computed, and it does all the scaling and the rotations and the movement if I tell it to do that. Huh? Make sense? How much time?
Minus 2 minutes.
Well.
You have to go back in time and edit.
So going back in time is one of the things you cannot do with the
You have to add another coordinate.
matrix. Another thing you can do is perspective. That's a different operation.
Nice.
Which I've cheated a bit here, but it's also numbers, but it's not the transformation. Okay, thank you. Do you have any questions? Sorry, no time.
I have some questions. Well, what are you using to visualization? Especially in explain window.
So
it is some visualization library.
So the visualization library is called Piglet. It's basically lets you do graphics that wraps OpenGL. And the rest of the stuff I've spent 2 evenings working, and it's some of the messiest code I've written. So yeah.
So
I've hacked it together.
The interactive where you change the value of the matrix. This is implemented in your code.
Yes.
Okay. Thanks.
I would like to make a library out of this stuff to make it useful. But
Is it possible to share this example also with the video?
oh well, you probably don't want to read this code.
Not this, but only the matrices.
Okay. Yeah.
Yeah, if the examples you showed to us, if it's possible to share it somewhere.
The video will be up someday. And if I don't put any code there, just comment on the video.
Okay.
Fix that. Okay, thanks.